Now my B3 lip QZ jobs are finished, so I can put the energies there. This is the gem energy. I switch from the term MOBA term to this one because all my calculations are now done, and this is more easier to copy paste from. So this is gem. Let me write the method's name. It's B3 lip def2 QZVP. For the trans, sorry, the trans has to be here. And the cis is next. Here is the cis energy. So this is just the electronic energy. And if I add it with the other contributions, and of course this is relative values will be all 0 anyway. Here also so you see the values little bit improve for the trans one once we go to B3 lip. If I do for the cis also, even for the cis values. So basically going to the hybrid functionals actually improves the free energy, relative free energy values. Now you can see that what we did here is that we did the optimization and the frequency calculation. That means the thermochemistry analysis on a method which is of much lower level than my single point energy calculation. Question may be that how good is this approximation? So to understand that, the only way is to do this optimization. These optimizations are quite expensive. I leave it to you as an homework problem, but remember each of these optimization for me at least took an hour for my laptop. If you able to do it, you do it. If you cannot, then maybe I'll put the values in the Google group just to give you an information how good the number comparison actually looks like. Now let us look at the MP2 and the B2 lip values. The MP2 values, first let us the input file, because RIMP2 of course you have to use RIJ cos x because any MP2 precedes with an Hartree-Fock step. So you need to use RIJ cos x for the Hartree-Fock, and for the MP2 it is RIMP2. You need to use an auxiliary basis. We have used def2 QZVPP/C. And you can do the calculation. So I can put the output file, so one advantage of doing MP2 is that you also have the Hartree-Fock contribution. So we have written among the methods how much is the Hartree-Fock value that we can get from an MP2 output file. So let me copy both. So this is my SCF energy. And this is my MP2 energy. So MP2 energy will be at the end. So final single point energy. I add the contribution from the Hartree from the thermal, rotational and vibrational modes and get the total. Get the total free energy. Of course, the relative free energy would be 0. Let's do the same thing for the trans isomer. This is the SCF energy. This is the final single point energy. Actually, you can see that here in the wave function based methods, actually the trans contribution comes pretty good. The experimental value is actually 5.3. So in a sense, this gives pretty good agreement with the experiment. Now let us look at the cis. So this is the SCF energy. And the MP2 energy is here. So now if I add the other contribution from translational, rotational and vibrational, this will be my free energies and this will be my relative stabilities. So if I compare with the experimental values, the MP2 numbers are actually in quite good agreement. Okay, so we have done up to MP2. Now let us try the last one, the double hybrid. As you can see, here's a lot of files. So it's generally a good idea to, for each separate calculation, if you make a folder and subfolder of this. I had one of my colleague who used to write every path and the folder for every job calculated on a copy or a diary. I believe that's a very good idea. If you are doing a calculation, there should be a notebook where you can go back if you want to retrieve all your results, so you can find out them in all places. Okay, now let's go to the B2 plib things. Let's go to the gem to B2 lib. This is the output file. So this is the final single point energy. This I will copy. The name of the method is B2P lip def 2 QZVP. Okay, we have not, I believe, discussed the structure of the output file. Before, let me copy the energy. And the important thing, I wanted to show you how the input file should look like in case there is any confusion. Don't forget, it's a double hybrid functional. So, like an MP2, you have to give an /C basis. So, this is given here. Now, if I add to the thermochemistry contribution, this is my total energy. Of course, this is 0. Now, go to the trans isomer. Then it is always a good idea to at least see the first few lines, because the input file is printed here. So, if there is any wrong input, something wrong obviously in your input file, you should have a look into it. Okay, let me go to the final. This is the energy of the trans, the thermochemistry contribution, total free energy, and this is the total free energy, and this is the relative free energy. It's 3.14. Let's now check the sys1. It's called sys P2P lip. So, at least the output file looks fine to me. And this is the final single point energy. I add the thermochemistry contribution, this total free energy, and this is relative free energy. Now if I look with respect to the experiment, it is 5.3 and 10.0 kilojoule per mole. So, the MP2 looks slightly at better agreement, but as you have seen that the basis set is actually increasing the contribution a little bit. So, what is 5.9, if you go to the CBS limit, it will be like 6 point something, and this will be 10.3. So, this will look like 8 when you go to the CBS limit, and this may look like 4 point something contribution. So, in a sense that the MP2 and double hybrid numbers are very close, and if it is below 1 kilojoule per mole, then it is not worth considering, because isomers which are within 1 kilojoule per mole, I will call them degenerate, because they are outside the calculation of any theoretical methods. So, they will be outside the contribution what you can calculate in any theoretical method. So, I will not make any conclusions if they are within 1 kilojoule per mole. I will just call them degenerate. Now, up to all the discussion we done up to now, so in all of the cases, at least maybe except maybe the first one, for all these things, 1, 2, 3, 4, 5 examples, I have done the optimization and frequency calculation at a much smaller level than at which level I do my single point calculation. So, these are the optimization and frequency calculations were done BP86 def 2 SVP, and the single point calculations were done in def 2 QZVP. It is BP86, B3 lip, hat fog, MP2 and B2P lip. Question is that if I have done the optimization and the frequency calculation as the same level as single point energy calculation, does that really change anything? So, to answer this question, we have also optimized this geometries in B3 lip def to QZVP. Maybe I should write opt also def to QZVP. Now, these calculations can be costly. So, I have done it beforehand, and actually, to be really honest, these calculations were done in a workstation. So, even in a workstation, although I have run them serially, it take around half an hour. So, in your laptop, each of the calculation will take 1 hour. If you are interested, you can do that. So, if I do both the optimization and the frequency calculation at def to qz bb3 lip, so this will be my thermochemistry contribution. So, I add it here. Now, you see this values is slightly larger than, and this is in atomic unit. So, this is slightly larger than what you get from the def to SBP BP86 calculation, but let us see how much is the actual contribution when it goes into the relative free energy calculation. Do not forget, is 262.5 we are taking as the conversion factor. So, if I take this, if I just do a rough calculation, it is around 0.05. So, it must be 26. So, this must be around 13 kilojoule per mole is the energy difference between these two thermochemistry contribution. But let us see how much is the difference in the relative thermochemistry contribution. So, let us first add the energy. Remember, this is just the thermochemistry contribution to get the energy as it is. This is my final single point energy. So, this is my total free energy, and this is my, so at the free energy level it is still 0.03. Now, let us do the same thing for the trans. So, here you will also see a similar trend. The thermochemistry contribution is slightly higher than what you got at def to SBP BP86, and if I now calculate the single point energy, so this is my total free energy now. So, also this is 0.03 electron volt higher than what you get if you just consider this one. Not, it's actually not 0.03, it's actually even less than that. If you see, this was the B3 lip energy. So, this is actually the difference is actually quite small, and if I consider the relative one, this is 1.16. Now, see what was the free energy difference when I have optimized at BP86 is 1.25 kilojoule, 1.26, and this is 1.17. So, it is 0.01 kilojoule per mole is the difference between the two free energies. One is optimized at a lower level and one is optimized at a higher level. So, we told that anything is below 1 kilojoule per mole is beyond the accuracy of the theoretical calculations. So, doing optimization at a much smaller level is perfectly fine in most of the cases. Now, let us quickly look at the cis one. So, this is the cis but. This is the thermochemistry contribution. let me add the electronic energy. Add it up to make it a free energy, and this is the relative free energy. 6.44, 5.90, it's still less than 1 kilojoule per mole. So, it's generally it's perfect to if you just use optimization and frequency calculation at a much lower level method, but don't forget optimization and frequency calculation has to be done in the same level, otherwise the frequency calculation and thermochemistry analysis has no meaning. So, as a homework problem, your homework problem will be isomerization energy between acetaldehyde and oxidant at standard temperature and pressure. So, you will do the optimization using BP86 def to SBP and single point using B3 PLIP def to QZBP. Just to give you an idea how much is the experimental value, it is 1 on 8 kilojoule per mole, and you can see that how good your numbers are. Maybe you come up with a strategy which will give you better agreement with experimental results. The other important thing is that up to now whatever calculations we are doing is at room temperature, it is 298.5. So, if I want to do the thermochemistry analysis at a different temperature, so how I can do? First thing I can do is temperature by giving a temperature keyword in the frequency block like this, and this will perform thermochemistry calculation at every temperature given. So, you will see a lot of this output one after another. Thermochemistry analysis has been done. Other option is that if you have already done your calculation, what you should do, you should use an input file like this. So, where you give the keyword print thermochemistry and geometry block, you give the initial Hessian name as whatever the Hessian obtained from your already run calculation, and now you give the frequency keyword with different temperature and XYZ file name. So, then it will what it will do, it will just do the thermochemistry part, it will not rerun the Hessian, it will just do the thermochemistry part using an existing Hessian, and you can get your output much more quickly. Now, question is that which temperature you should use for thermochemistry calculation. It depends upon at which temperature your reaction is performed. So, whatever at temperature your reaction is performed, you should do the thermochemistry analysis at that temperature only.